Today on ScienceSketch, we're going to dive into stereochemistry and how to assign R and S descriptors to stereocenters. If you have a chemical structure of, say, adrenaline, is it R or S? Well, first, let's define some terms. Two compounds are stereoisomers if they have the same atoms and bond types, but have a different arrangement of substituents in 3D space. If we have a carbon with 4 substituents, we can have 2 configurations. We see that these 2 molecules cannot be overlaid. If we align the yellow and red spheres, the blue and magenta ones do not line up. If we align the blue and magenta spheres, the yellow and red ones do not line up. They are different. In fact, they are mirror images of one another. We call mirror image stereoisomers enantiomers and use R or S to describe which is which. When we draw structures on a piece of paper, we use wedges and hashes to show the orientation of the substituents. A wedge bond is sticking out at you, and a hash bond is facing away from you. It is important to get in the habit of visualizing wedge and hash structures as actual three-dimensional shapes. Nobody was born with this ability. You have to practice it. Why is stereochemistry important? It is critical to have an unambiguous way to describe stereochemistry because 2 stereoisomers can have different properties. One stereoisomer may be a life-saving medicine, and the other may have no effect or may even be harmful. Thalidomide is a notorious example. R-thalidomide is a life-saving and effective sedative. S-thalidomide is a teratogen, that is, it causes birth defects. Tragically, it was a mixture of the R and S enantiomers, also called a racemic mixture, which was sold in the 1950s as a treatment for morning sickness and caused birth defects in thousands of infants. Picking the correct stereoisomer is important in the flavor and fragrance industry too. R-carvone is found in spearmint leaves and has a sweet and minty scent. Its mirror image, S-carvone, found in caraway seeds, has a spicy, earthy smell and is added to rye bread and other baked goods. R-limonene, found in lemon and orange peels, has a citrus smell, while its enantiomer, S-limonene, has a pine or turpentine smell. We use the CIP rules to assign R or S stereochemistry based on the chemical structure. Keep in mind that the R or S descriptor has no basis in physical laws or chemical properties. It is simply a universally accepted method to establish the orientation of substituents in 3-dimensional space. Let's see how it works. To determine R or S stereochemistry, all you do is assign priority to each substituent. Orient the molecule so that the lowest priority, 4, is facing away from you, and then simply count 1, 2, 3. If the rotation spins to the left, counterclockwise, then it's S, sinister, Latin for left. If it spins to the right, clockwise, then it's R, rectus, Latin for right. The priority is based on the atomic number of the atom bonded to the stereocenter, with H being 1, carbon being 6, nitrogen 7, oxygen 8, and so on. If there's a tie, say there are 2 carbons bonded to the same stereocenter, then you go out 1 more bond and keep going out until there's a difference. Let's look at an example. Here's one of the 20 amino acids that make up proteins, alanine. Sometimes you will see structures drawn without all the hydrogen showing. The amino substituent and the carboxylate are in the plane of the central carbon. The methyl is pointing out of the plane, and therefore hydrogen is pointing backward. The carboxylate carbon, because it's bonded to oxygen, is higher priority than the carbon that's bonded only to hydrogens. With the H placed in back and counting the other substituents, 1, 2, 3, we see that it spins to the left, therefore it's S. All the natural amino acids have the same stereochemistry, except for glycine, which is symmetrical and has no stereocenter. The RNS rules work the same in cyclic molecules. Place the lowest priority substituent in the back. For the structure on the left, there are 2 methylenes bonded to the stereocenter. Moving out 1 more bond, we see that the carbon bonded to the oxygen is higher priority than the carbon bonded to another carbon. So the order is 1, 2, 3, making it R. Just because an organic compound is drawn with wedges and hashes doesn't make it chiral. The molecule on the right has a plane of symmetry. It is identical on each side of the structure. You cannot assign R or S stereochemistry to a symmetrical molecule. This compound has two asymmetric centers. Starting with the one on the left, H is facing away from you, so 1, 2, 3, it is R. The other stereocenter has the H sticking out toward us. It's backward. You could redraw the structure so that the H is facing away, but that takes time. This is the time to apply the switch rule. If the H is facing the wrong way, then simply reverse the rule, counting from high priority to low priority, 1, 2, 3, and reversing the rule, it is R. Okay, well, what about double and triple bonds? How are those handled? In this case, we add what are called phantom atoms, so carbon double bonded to oxygen is counted like this. Carbon bonded to 2 oxygens is higher priority than carbon bonded to only 1 oxygen. Therefore, this one is S. A carbon-carbon double bond is counted as if each carbon is bonded to a phantom carbon. A carbon bonded to 2 carbons is higher priority than a carbon bonded to 1 carbon. Therefore, this has S stereochemistry. Triple bonds work the same way. A nitrile is counted as if the carbon is bonded to 3 nitrogen atoms, making it higher priority than a carbon bonded to only 1 nitrogen. 1, 2, 3 clockwise, so the stereochemistry is R. Here's a structure with an asymmetric carbon and a carbon-carbon double bond. Based on the rules we have learned, it is designated R. Easy enough. The orientation of the double bond gives us 2 possible geometrical isomers, and the CIP rules are used to describe these also. If the 2 highest priority groups are on opposite sides of the double bond, it is designated E from the German entgegen, meaning opposite. If the 2 groups of highest priority are on the same side of the double bond, then it is assigned Z from the German zusammen, meaning together. Let's look at a couple more examples of E and Z pairs. Highest priority on the same side, it's Z, opposite side, E. Highest priority on the same side, it's Z, opposite side, E. Okay, well, what about this bad boy? This is an opiate called morphine, isolated from poppies. First, you want to draw the implied hydrogens. There are 5 asymmetric carbons in this structure, and you can assign R or S to all 5 using the rules you have learned. Most of these hydrogens are sticking out towards you, so you'll definitely want to apply the switch rule rather than drawing the whole molecule again. Starting with this carbon atom, the highest priority substituent is going to the oxygen. Looking at the other substituents, the carbon bonded to an oxygen is higher priority than the one bonded to a carbon, so it's 1, 2, 3. Applying the switch rule makes it R stereochemistry. You can do the rest. Check yourself. You should get the following R and S assignments. We hope this video has provided a foundation in your understanding of the CIP rules for R and S assignments and EZ geometrical isomers. If you want to see more ScienceSketch videos, please click the subscribe button.